This is a demo of the move instructions in the single cycle computer. In the library, open up a VLA, viciLab application file, move register to register, register to special function register, data pointer, SFR special function register to register, and move from import. Select this. This opens up a series of tabs that show the digital hardware inside the single cycle computer that is relevant for each instruction. Enter your password. This takes a few moments to configure a remote FPGA. Look in the icon below and open the window with lots of tabs. Back to the IDE and open an assembly program. In the SCC GUI test programs folder, the move assembly program. Here, register 4, bit 13 is set. This is used as the data to transfer then between registers. The first instruction after this is register 4, data is transferred to register 5 using Movrr register to register. Then register 4 is transferred to special function register 9 and then special function register 4. Then a value in the instruction is written into the data pointer, which is special function register 15, and that is then transferred to register 4. Then a loop executes which reads the import, which is a byte, into register 3 and then tests if it's greater than 0 and continues to loop around until it's a non-zero value, and then the program ends. So assemble the program, transfer to instruction memory, list of instructions from 0 to 8, ending with end. The first instruction is to set bit in a register just to put the value into register 4, 2000 hex. The first move instruction is R4 to R5. So this is the instruction and opcode for move register to register. The source address register is 100, which is 4. That's used in the operand fetch to select the register 4 value, which is currently 2000, through this multiplexer. There's other logic in the operand fetch. This is the active logic. So the bus A into the function execution unit has value 2000. The instruction decoder decodes the opcode, this one with a single bit asserted here, to deassert ALU function and arithcin. They select the 2000 input on the A bus through unchanged on F unit out. The instruction decoder also asserts register write. In the instruction, the destination register output, 3-bit register for R0 to R7 is 101, which is 5, and the star illustrates that the register that will be written to when the instruction executes is register 5, and it will take the value 2000. The program counter will increment from 1 to 2. So if I step the instruction, 2000 is now in register 5, here also. The next instruction is move from register to special function register. The source is register 4, the destination is special function register 9. The opcode is shown here, 7-bit opcode. The source address register is 100, which is register 4. That takes the value 2000 through in the operand fetch as the input bus A into the function execution unit. In the instruction decoder, this opcode deasserts ALU function, both bits, and arithcin, so they're not asserted. It does assert register write and also asserts select SFR bank signal. The red here indicates that a special function register write is occurring here rather than a register write. The star is special function register 0 to 7, 8 to 15, so this is SFR 9 is to be written when the instruction executes. And the address of the destination's SFR, because there are 16 registers, 4 bits are required. The fields in the instruction which define that R out, that destination register, are most significant bit, bit 3, 210. So it's distributed a little bit in the instruction. This is done automatically by the assembler, so you don't need to worry about it. It takes SFR 9 here, and this is the upper bit 1001. There are a couple of unused bits in the instruction also. So if I execute that instruction, the program counter increments to 3, to the next instruction here. This next instruction transfers R4 contents again, but now to special function register 4. The opcode is the same as before. The source address is the same as before. 2000 is passed through. It's again writing special function register. Cell SFR bank signal is asserted to select this as the destination bank rather than this, register right also, and the address of the destination register is 4. You can see that here, 0, 1, 2, 3, 4. And here, the address is 0, 1, 0, 0, which is 4. The program counter will increment from 3 to 4. And I single step. This instruction, move data pointer, has an opcode of 0001, and the remainder of the instruction, 12 bits, is used as the data value to be written into the special function register, which is a dedicated register SFR15, the top SFR register. 107 is the value, that's the 107 value here. SFR15 has an address of 1111. Select SFR bank as asserted as before by the instruction decoder, so also is register right. In order to take from the instruction bits 11 to 0 and put them into the single data path for writing to the register in here, there are some multiplexers inside the write back which require select instruction digits 2 to 0. These are the digits 2 to 0 in the instruction, and also select instruction or import. It pushes into the write back directly without having to go through the operand fetch or the function execution unit. So the instruction 12 bits are being used to write straight through to here. And you can see 107 passes through right to the special function register. And I step the instruction again. Now I'm taking the value in the special function register, which is 107. That can be seen up here, up there, and put it into register 4. Move SFR to R. Now only 3 bits are required for the destination address because there are only 8 R registers. Register right is asserted. Again, ALU function and RFC and R0 to pass the value through from the input bus A. But in this case, SFR15 is being taken through this multiplexer here. Its value is 107. And another signal is asserted by the instruction decoder called transfer SFR to A. And it pushes this through. And the source address RIA is bits 2, 3, 4, 5. 5 down to 2. Again, it's 4 bits because there are 16 SFRs. So the instruction format is a little bit different to support this instruction too. The 107 passes straight through the function execution unit. The red here indicates that the register bank R has been written to. Again, the program counter is incrementing. And single step again. Now there's an instruction called move in, which takes the import, which is 8 bits, and pushes it through this multiplexer, which is controlled by a signal cell instruction or import. It's related to the move data pointer. It uses some of that hardware, and it's taking this value through to write to the register bank. I can read the import and write it to the register bank. Reg write is asserted as before. The destination register address is 3. It's in the instruction as before, and a new opcode. This is writing to register 3 here, and the program counter is incrementing again. And this will continue to the next instruction. This is a jump of 0. So if register 3 is 0, it steps back 1 instruction. In this case, I don't have a JZ jump instruction tab, so it's not illustrating that. There's another video demo demonstrates jumps. I'm going to step again, and as long as there's a 0 on R3, it will continue to loop around here. So I'm just going to put the value 4. Any non-zero value on here will change this. And now register 3 has the value 4, and the jump of 0 will pass on to the end now. End program is asserted as before, and the program counter remains unchanged on every active clock edge. I'm going to reset once more, step through to the first move instruction, and select the function execution unit. And you can see now that the value 2000 is passing through here, straight through out on F unit out. I'll go to the write back, and in the write back F unit out path is the default path. You can see the stars here into either the register bank or the special function register bank. The cell SFR bank signal is not asserted. Therefore, it's selecting the register bank. And internally, these are signals inside the single cycle computer. This bank is selected. The destination register address is 5, as can be seen in the instruction here. And the value going into it is 2000. So if I step, again, I go back to the move R to SFR. I go to the write back again. In this case, the value 2000 passes through as before. but in this case select SFR bank is asserted. So there's an internal signal called write reg SFR. It enables access to this bank rather than this bank. And the destination address is SFR90, which is 789, and this will change. Within the special function registers is the stack pointer. If you look inside the special function register map, there are also connections to the LEDs, 7-segment displays, etc. So if I step again, R4 written to SFR4, SFR4 is connected to the 7-segment display. And if I write the value 2000, you'll see 2000. Step again and you'll see the value 2000 on the 7-segment display. The data pointer, if I look at the write back, the data pointer is here, the instruction value 107. Because the signal cell instruction digit 2 to 0 is asserted, this path is selected. Select instruction or import signal is asserted. It puts the value 107 through to here for the register write. But this is being written to the special function register, so cell SFR bank was asserted by the instruction decoder, as was reg write, so it goes to this bank. Step again and go to the write back. Now I'm taking the special function register 107 through again. It's similar to an example before, and I'm writing to the register bank. Now I'm looking at the move in port as before, and I go to the write back. And the move in port is this byte, and it's selected through this path. So the signal cell instruction digits 2 to 0 is deasserted. It selects this path. The signal select instruction or import is asserted, and it pushes it through to here. And I'm writing now into register 3. You can see that register write is asserted, and select SFR bank is deasserted, so the action is here on the register bank R. Just one correction, the note on the program should have read 7-segment display, upper digit, turns on instead of LED.